देखिए, मैं अभी कुछ महीने पहले तक रेगुलर क्लासेस अदिस अबाबा यूनिवर्सिटी में लेता था। पिछले 17 साल से मैं वहाँ MSc और PhD क्लासेस ले रहा था। तो मैं रूटीन मेरा करीब 2 घंटे की क्लास वहाँ होती है, तो 2 घंटे की क्लास लिया करता था। मैं कई साल से चल रहा था मेरा सिलसिला। उससे पहले मैं अलीगढ़ मुस्लिम यूनिवर्सिटी में 2004 तक प्रोफेसर था और क्लास पढ़ाता था रेगुलर। तो मैं पिछले करीब 59 साल से लगातार क्लासेस ले रहा हूँ। अच्छा, और लोग तो अपनी क्लास 1 घंटे की लेते हैं, जाते हैं, तैयारी करते हैं और उसके बदले में उनको बहुत पैसा मिलता है, दे गेट ह्यूज अमाउंट ऑफ सैलरी। अच्छा, मेरी तो अब सैलरी बंद हो गई क्योंकि मैं बीमार पड़ गया था पहले 4 महीने पहले। आई गॉट स्ट्रोक, ब्रेन स्ट्रोक। उससे पहले भी मुझे ब्रेन स्ट्रोक हुआ था 2009 में। उससे पहले मैं 79 से हार्ट पेशेंट हूँ। बाईपास हो चुकी है मेरी 2002 में। एंजियोप्लास्टी हुई 2015 में और 2009 में लेफ्ट साइड का मुझे स्ट्रोक हुआ था। मैं रिकवर कर लिया बहुत जल्दी। अभी फरवरी में मुझे फिर जैसे ही अंगारक दोष लगा था, शनि का मंगल का, 28 फरवरी को मुझे स्ट्रोक हुआ और मुझे लगा कि ये तो मेरा अब लास्ट टाइम है, अब तो मैं शायद नहीं बचूंगा, क्योंकि उम्र भी मेरी 80 करीब हो चुकी है। मैंने कहा ठीक है, अब तो जाना ही है। तो मेरे दिल में अभी ये रह गया था, मैं जाते जाते कोई किताब लिख लूँ और मुझे टाइम नहीं मिला किताब लिखने का, क्योंकि मैं तब से बराबर समझता हूँ रेगुलरली गाइड, रिसर्च गाइड एंड टीचिंग, तो किताब लिखने का वक्त ही नहीं मिला। एक्चुअली मैं रिटायर होता अगर उसके बाद खाली होता तो किताब लिखता। मेरे साथियों ने किताबें लिखी हैं तो मेरी बहुत इच्छा थी, लेकिन मैं वो कर नहीं पाया। अब मेरी उम्र 80 के करीब हो चुकी है, तो अब किताब लिखने का थोड़ा सा उतनी हिम्मत नहीं पड़ रही। तो मैं अपने को कैसे बिजी रखूँ? अब तक तो मैं 2-2 घंटे की क्लास लिया करता था, अब मैं खाली हो गया। तो मैं अपने को खुश रखने के लिए, जैसे तुलसीदास ने रामचरितमानस लिखी, स्वांता सुखाय जरूरी, अपने मन को सुख देने के लिए। तो मैं अपने आप को बिजी रखने के लिए, अपने आप को अंतःकरण को सुख देने के लिए मैंने ये सोचा क्यों ना मैं वीडियो बनाऊं। उसमें मेरा वीडियो बनाने में, तैयारी करने में 2 घंटा लग जाएगा, फिर बनाने में, फिर उसको अपलोड करने में 3-4 घंटे लग जाएंगे टाइम टोटल। तो इससे मैंने यही सोचा कि मैं बिजी भी रहूँगा और जैसे रोजाना वहाँ यूनिवर्सिटी में तैयार होकर सुबह जाता था और रेगुलर टीचिंग थी, वो उसके बदले मुझे सैलरी मिलती थी। नाउ आई एम विदाउट पे, बट आई वांट टू कीप माई सेल्फ बिजी। तो कैसे बिजी रहूँ? अब मुझे जो आता है, मेरा शौक कुछ बचपन से आता है, एस्ट्रोलॉजी में, होम्योपैथी में, पामिस्ट्री में, वो सब मुझे आता है। पर पामिस्ट्री तो जब यहाँ आदमी सामने आएगा तभी हर देखा जाएगा उसका। ऑनलाइन जरा मुश्किल होती है, बहुत बारीकियाँ रेखाओं की नहीं पता चलती हैं। न्यूरोलॉजी का भी शौक था मुझे, लेकिन एस्ट्रोलॉजी का भी शौक था, तो इसलिए मैंने एस्ट्रोलॉजी के वीडियो बनाए और मैंने सोचा कि क्यों ना फिजिक्स मेड सिंपल के नाम से बनाऊं और मैं फिजिक्स के फिनोमेना जो मैंने अब तक पढ़ाए हैं और जो मुझे याद हैं, जो मेरी समझ में आए, उनके बारे में क्यों ना मैं लोगों को बताऊं। तो मैंने अपने YouTube पे वीडियो डाल रहा हूँ। मैं तो अब मेरा अंतिम टाइम आ चुका है, पता नहीं कितना टाइम और है, लेकिन तब तक ये कुछ वीडियो शायद लोगों के काम आ जाएगा, जो लोग पढ़ें कभी। क्यों किताबें पढ़ने का रिवाज अब बहुत कम हो गया है। किताबें लिखना भी अब केवल लाइब्रेरी की तो ठीक है, बाकी किताबें कोई नहीं खरीदता, क्योंकि हर चीज़ तो इंटरनेट पर, गूगल पर अवेलेबल है। इसलिए मैं ये सोचा कि मैं क्यों ना अपने टीचिंग वाले वीडियो बनाऊं, तो जो मुझे याद है या जो मेरी समझ में आता है, जो मैं समझा, उसके बारे में मैंने ये वीडियो बनाना शुरू किया। शायद आप लोगों के लिए यूजफुल है आगे चल के। तो माई टूडेज टॉपिक इज आई एम गोइंग फर्दर फ्रॉम सिंथेसिस स्पेक्ट्रोमीटर। I told you that the drawback of sodium iodide synthesis spectrometer is that peak is broad, that is delta E is large, delta E over E. We have to reduce this delta E over E somehow. If this is reduced, the evolution of the system will be good and we can resolve closer peaks, gamma ray, because gamma ray have many closer peaks from the excited states. And we are getting only envelope of many peaks by sodium iodide. We are not able to resolve. We can resolve if they are far apart. Energies are far apart. But closer energy, not possible. So to reduce the pulse width We have to do something. So that is, now I will go to the semiconductor detector, so semiconductor counter. So I will talk about so under the heading of semiconductor detectors, remember that these were not available when I was a student. They came very after, maybe around 63, 64. They just discovered at that time. They were in use in 70s only. So semiconductor detectors, what are the semiconductor detectors? How they are used for the gamma rays or charged particles? So I will try to explain you. And how to reduce the pulse width. So semiconductors, we know, first of all I introduce you that in the beginning people took some crystals, say like diamond crystals, you can take cesium and cadmium sulfide. These crystals, you see there are mostly these are insulators. These crystals, diamond, or cesium, cadmium sulfide, they have energy gap. This is around, in diamond it is about 5.8 electron volt. 5.8 electron volt. So these are insulators. In fact, these insulator means this is a valency band and this is a conduction band. And this much is the forbidden energy gap. So what the meaning of forbidden energy gap? Means nothing is there. It is no charge, no electron, free electron there. Valency band, all the most electrons are here, and when you supply some energy from some radiation or by electric potential, well, some electrons from valency band can go to the conduction band. Suppose few electrons come here, few electrons come here. So when we apply some potentials, across two ends of a crystal, like cadmium sulfide, which is insulator and has got, say, around, you can say this 5.5 electron volt band gap. So this is insulator. Insulator means we have good conductors, we have large number of electrons are available for conduction, metals. We have bad conductors. So insulators, there are no electron available in the conduction band for the current to flow. When we apply some potential, there is no electron, no current flow. But if you supply some energy, and by that energy, by radiation, some electrons go to the conduction band, then some electrons, if energy is supplied by a radiation, some electrons from valency band can go to conduction band. and under a potential applied and under an electric field. Under electric field, current can flow. Which may give electrical pulse. So in the beginning, these crystals were used by many people to see the effect of radiations falling on these crystals, and the radiation gave energy. Some electrons were free, they came to conduction. When they apply a potential through a resistance, the current was flowing, and that it gave IR drop, and we got some very small electrical pulse because the number of electrons in conduction band was very, very small. So these insulators type crystals, in the beginning they were tried to use as, this is called as ionization counter. Ionization counter using a crystal. But this is a very, very small pulse, so not useful. So insulators, not useful. You know, metals are good conductors, have large number of electrons free, so they cannot be used. They don't have energy gap, so they cannot be used for the detection purpose. So this energy gap, if we see some semiconductors, what are the semiconductors? Semiconductors which are very used, too much used now, semiconductors in nature, first was say silicon and then germanium. Silicon, you see, this is probably charge 14, this charge 32, probably 14, silicon 28, this may be 72, germanium. So this germanium has got Z32. Germanium having Z value that you can write by capital Z because small z we write for Z equal to 70, Z equal to 32. This will have larger probability of gamma interaction. Larger than silicon, because silicon is having 14 Z. So, as you know, photoelectric effect, this is proportional to fifth power of charge. So this germanium very useful for gamma radiation due to the higher value of that. Silicon can be used for other radiation. So silicon and germanium, two semiconductors. These are semiconductors because these semiconductors have the band gap. This you can see if I write Eg, band gap, orbital. This may be around 2 to 3 electron volt. Two to 3 electron volt. So this valence band and this conduction band. So, Here, you see, 2 to 3 electron volt band gap. So radiation falling on us. This crystal can give its energy, and then more number of. This has got band gap is small, so it is easier to raise the electrons here. More electrons easily by small energy. And these electrons are now available for conduction. Current will flow. Semiconductors are better than crystal insulators like. But remember, this semiconductor, silicon, germanium, these are pure intrinsic semiconductors. These are intrinsic. Intrinsic semiconductors. What are intrinsic semiconductors? Pure material means germanium having 4 valency electrons, silicon having 4 valency electrons, and the crystal lattice silicon or germanium is situated at certain distance. So these are the pure intrinsic. Remember, these are intrinsic semiconductors electrically neutral. I have been posing a question many times to the students in the class, also in Ethiopia and here also in Aligarh. And also I have been posing this question to the in the interviews of assistant professor, etc., to many PhD holders. One question I will ask here you also, that we know intrinsic semiconductor. These are what intrinsic means? Pure. Having very small impurity, negligible impurity. Impurities are always there, but we call them pure. There are some semiconductors which are called P-type. P-type germanium or P-type silicon. Similarly, we have N-type germanium or silicon. Well, what the difference in the P-type, N-type and intrinsic? As you know that pure germanium crystals, say, or silicon crystal, we have here in the crystal lattice, say we have, say, silicon or germanium. These are sitting here. So if this is a silicon, it has got 4 valency band electrons, outermost electron, valency. It is also silicon. Similarly, they have 4. This also has got 4. So these electrons have covalent bonding, 1 electron of this. They have covalent bonding, 1 electron. Covalent bonding, electron of this. So all the 4 electrons of germanium or silicon, they have handshake with the nearby electron. That is the covalent bonding, strong bonding. These bonding are broken by thermal excitation or by heating. So at this time, this is intrinsic semiconductor. There are no free electrons or very few free current carrier. Means electron. Because all bonds are, all electrons are having handshake. The bonds are not broken. If somehow, say, this also silicon, this also having silicon, this also having bond, this bond. Somehow this bond is broken, then this becomes free. This electron become free because they don't have bonding. So this electron is free to move. So by thermal excitation or certain temperature heating, these bonds are broken. Then the electron becomes free, and then these electrons have negative charge, and they are available for the flow of current. When we apply potential across this, and current will flow. Because in intrinsic semiconductor, the free electrons are very, very small, free charge carriers. In intrinsic semiconductors, the free charge carriers, current carriers, charge carriers or current, flow current are very, very small. Few electrons are available by thermal excitation. Bonds are broken. So these intrinsic semiconductors are not very useful. So these are not useful as radiation counter. So these are not, because current flow very, very small. So now what we do, we make this as, say, N-type semiconductor. So what is N-type semiconductor? What I do, in place of this silicon, I introduce, when growing this crystal, I introduce a small impurity. Introduce a small impurity of fifth group of the periodic table. Suppose arsenic. I introduce arsenic here. So arsenic has got 5 electrons, valence electrons. If this silicon is replaced, say, by arsenic, this is the arsenic. Arsenic has got 5 electrons, so 4 are having bonding with the nearby electrons of silicon or germanium they have. But 5th electron is free. In this way, by introducing more and more arsenic atoms, we are introducing a free electron. This material is called donor. It has donated an electron from its balancing band to the system. So 5th group arsenic, this gives additional, this gives each atom of arsenic is given one free electron. In this way I get many, large number of free electrons. This type of material in which I have introduced large number of free electrons, this material is called N-type. Now N-type silicon or N-type semiconductor. In which large number of current carriers that is electrons are available. This N-type material in which we have introduced 5th group, arsenic is called donor. it has donated an electron to the system. It has made many electrons free. So these are available. So what we have in n-type material semiconductor, large number of current carriers, electrons are available. And where, so this electron, you apply potential, this electron will flow and current will flow. This will go to the next. Means this will be broken and then this becomes free, this electron fills this place and this electron becomes free, like that. The current flow means electron goes to the next atom, next atom, next atom. So donor material is arsenic. In place of arsenic, if I introduce a third group element, say phosphorus, aluminum, phosphorus, having 3 electrons. So one is having bonding, one is having bonding, one is here. This electron is free, this electron is not there. There is a deficiency of electron. Phosphorus, third group element, has got 3 valency bundle, 3 valency electron. So one bond is incomplete. What we have? One bond incomplete means there is one deficiency of electron. The deficiency of electron theoretically is given name a positive particle hole. So deficiency of electron means hole. That is positive particle. Hole of positive particle means there is no electron. So deficiency of electron. If electron is available, it will fill this vacancy. So what we have? By adding more P phosphorus, what we are doing? 3 electrons are having bonding, but 1 electron is there, deficiency, bond is not complete. So this type of material is called, where we have introduced a deficiency of electron, that is theoretically positive particle, we call it P-type material. This is because this will accept one electron. If electron is free available, it will fill this vacancy. So this is called acceptor. Donor and acceptor. Donor means 5th group material which has got 1 extra electron. Donor which can receive a 3rd group material which has 1 less electron. No 4, only 3. So 1 deficiency, that is theoretically talked as a positive particle, a hole, a deficiency. When current flow, when this bond is broken, suppose this electron fills this and this completed. The hole passes now here. Then this electron fills this vacancy, a hole passes. So like that hole passes from this side. Electron comes to this side. So there is a flow of current in this P-type material, P-type silicon or germanium, P-type semiconductor. Holes are majority current carrier. And electrons are minority current carrier. So what we have? P-type material, large number of, that is majority, large number. Don't be confused by minority majority in the country. We have minority majority. So don't be confused. These words are simply to say majority means large number of electrons. Minority means small number of electrons. So majority current carriers in the N-type material are electrons, while majority current carriers in the P-type are holes, deficiency of electron. There may be some broken bonds that may give you minority current carriers here also, electrons in minority by broken bonds. And here also there may be N-type material, there may be also minority current. Majority are electrons, minority may be holes. In this P-type, majority are holes and minority are electrons. So both the current carriers are there, but majority are P-type material, holes, and N-type materials, electrons. So this P-type has got large number of holes. Now I have so P-type has large number of positive particles, that is hole, and N-type has large number of electrons, so negative charge. Now there is a simple question. Intrinsic semiconductor is electrically neutral. What about extrinsic semiconductor, P-type and N-type? I have asked this question several times in my class to the MSc students, even to the PhD students, even in the interviews of assistant professor post. PhD degree holders, when they come for the interview, I ask this question, that intrinsic semiconductor is electrically neutral. What about extrinsic semiconductor, P-type, which has got large number of holes, positive current carriers, N-type, which has got large number of electrons as current carriers? I say that answer this question, you think for a moment, 1 minute, 2 minutes, and then answer. But the most of the students, about 99% of students answered immediately without thinking. Even in the lectures interview that, sir, P-type material is positively charged, N-type material is negatively charged, because it has got more number of electrons free available and P-type has holes. Then I again repeat, then think again how the system becomes charged. What you do when you want to charge a system. I am saying intrinsic semiconductor is electrically neutral. What about extrinsic? What you have done? You say that charge produced. So charge produced, okay, there is free charge available for flow of current. But when the body becomes charged, what you do? Either you remove the electrons from the atom or you add the electrons. When you remove the electrons, the system nucleus becomes positively charged because electrons and protons are equal in number. When you remove electron, it becomes less electron and more protons, so it becomes positive charge. If you add electrons from outside, it becomes more negative, proton number is same, electron number increases, so it becomes negative charge. So, making a system charge, either you remove the charge or you add the charge. Yes. So what you have done when you have made P-type material or N-type material? Have you added some charge or have you removed some charge? Oh, no sir, no sir. Then you are mixing a neutral material, arsenic or phosphorus, in a neutral material, silicon or germanium. So this neutral silicon, this phosphorus neutral, you are adding this when growing the crystal. So both are neutral, means proton and electron number same. Then how they become charged? You are not adding any charge, you are not removing. You are adding equal numbers of protons and electrons in an atom of phosphorus or arsenic. So all 100% of students answer this question wrong, but when we explain them how the system becomes charged, and if intrinsic semiconductor is neutral, no doubt, but extrinsic is charged, how to carry that? how to carry that extrinsic silicon wafer or extrinsic germanium wafer. If they are charged, you cannot carry them. Charge cannot be, how you will insulate them? We put our hand, this p-type material and that material. So then they understand, yes, because we are not adding any charge, we are not removing any charge, we are adding a neutral material in a neutral material. So extrinsic semiconductor is also electrically neutral, not charged. Okay? Now we have say, what we have? I have say a p-type material suppose. And I have here an n-type material. This is P. This is n-type. Means this has got large number of holes available for the conduction. Holes are there. Like this. In this you have large number of electrons available for conduction. So we have made a junction, just like junction diode. When we are growing crystal, on one side we grow, if we had phosphorus material in the silicon, so a P layer is formed, other side N layer is formed, and we have junction, this is the junction. Now what we do? We apply, say, a potential, a battery connect here, then this is negative terminal. And this is a positive terminal. Such type of biasing, this is called biasing, means you apply potential on the junction diode. So this is called reverse biasing. You are biasing your junction diode by a reverse potential, means plus side you apply negative potential, this side you apply positive potential. Or first let me explain, also I should explain the forward biasing. This is junction and this is plus, 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 hole. These are our holes. These are electrons. So these are electrons. And these are holes. So these are the positive particles, theoretical particles. Deficiency of electron, we call it as a positive particle. It is a hole. And we have now a forward biasing at the junction. We connect a battery, this is positive and this is negative. We make a connection like that. What will happen? I will put certain resistance also support in the circuit. We put, so that current can be controlled. Some resistance can be, so current can be controlled. Current is not large. Okay? So, I have put positive potential terminal of battery, say, simple dry cell, I connect suppose here. This is the positive end, positive field. This positive potential terminal, what will do? Apply a force on the holes, and the holes will move under the force, under the influence of this potential. The holes will move towards the N-type material. This is N-type, this is P-type. I have applied negative terminal here. So under the field, negative terminal here, the electrons will get a repulsion and they will move to this side. So hole start moving this side and electron start moving this side. That is called diffusion of charge. So positive going to this side and negative coming. When negative coming to this side, suppose, and positive coming to this side, some negative coming, some positive going there, some positive. What happens? Negative combines with this positive. So this becomes one hole combines with electron. It means this side, if one or two or three holes combine with the electron, the positive charge decreases. So this becomes, system becomes negatively charged. Means maybe somewhere I draw a line here. A potential is, because this electron coming here, neutralizing a hole becomes less positive charge, the system becomes negative, and positive holes coming this side, neutralizing neutron, electron, so this becomes positively charged. So there is a positive, you can say this side becomes positive. So what happens? Some holes migrate to this side and some electrons go to this side. So these electrons combine with some hole. Hole number decreases, and in this side hole number decreases, this side electron number decreases, and at the junction a potential barrier is created. This potential barrier stops further migration of, because this negative, if electrons are going this side, this will repel, this will not allow further diffusion of electrons. If holes are going this side, this positive will not allow the holes to move this side. So when we make a junction and we connect a battery like this is called forward biasing. There is a potential barrier developed which further stops any further migration of the charge, and charge diffusion stops. And this region, a small region, becomes charge free. In this region there is no free charge. Charge free. Further diffusion stops because a barrier is created. Very small barrier that stops of further migration. Maybe less than an electron, less than 1 volt, 0.6, 0.9 like that. So this barrier created, and this layer is having charge free. Now this is called depletion. Depletion layer. A layer which has no free charge, depleted. Charge, free charge is depleted, means no free charge, and migration also stops. Migration will again start if you increase this potential more than this. If the potential becomes more than this, barrier is now finished and further migration starts. That is called current starts flowing, forward current starts flowing. forward current due to electron. This is current of the order of milliampere because large number of electrons are available here for conduction. So this is the forward biasing current is large. This is simply junction diode forward biasing. But if I reverse the voltage of battery minus this side plus this side, this is called reverse biasing. Means this negative field here will attract the holes to this side and it will not allow them to move that side. So means these are coming, positives are coming towards, they are going towards us, through them by the field. And these negatives are going through them to this side plus. So what happens is that at the junction, as the electrons are going to this side, holes are going to this side. So this layer, which is the depletion layer, again here, the depletion layer, this was very small here. Here it becomes larger because this negative field is not allowing holes to move to diffuse to that side. It is having force attractions. Holes are coming to this side, they are coming on this side. And then electrons this side. So larger, under reverse bias, depletion layer is large. Depletion layer is large. Depletion layer means there is no free charge in this layer. This depletion layer, which is the property of a junction diode under reverse bias, is a very good application in nuclear radiation detectors. How? If suppose a radiation comes here, any radiation, alpha particle, electron, gamma, anything, it comes here, material is there, where we don't have any free charge. So this will produce ionization, negative charge, and positive charge, because atom is neutral. So it will now ionize this silicon or germanium medium. Ionize means it will remove the electron and rest of atom becomes positive charge. So this is positively charged atom and this is free electron. So on this passage of, this is the charge produced by incoming radiation. The charge coming by incoming radiation this is the free charge electron. This charge can be collected or a current can flow by applying a potential through a resistance, a proper potential, so that the free charge, incoming radiation charge produced, the free charge can give you. So this forward biasing is not useful for the nuclear radiation detector. This is not at all, because its barrier, this is the depletion layer very small, and when we apply potential, this depletion layer is finished. So large depletion layer under reverse biasing of a silicon or germanium semiconductor can be used as a solid state ionization counter. A solid state ionization counter is simply a junction diode under reverse biasing. Junction diode under reverse biasing. So I have suppose a junction diode. I may make like this. So this is P type. From this side we introduce this hole is a P type material. This is very large, maybe smaller, maybe. Suppose we have some introduce N type. N type. This is the N type. What we have this N type, when we have reverse bias, means N is a negative. So we apply a negative potential here. So the resistance R, and we have this side as a positive terminal, and we have a capacitor here, C and R. This we get electrical pulse. What we do when a radiation comes? This region, this was N type, this is P type, and this is the depletion layer where there is no free charge. This is junction diode. Under reverse bias. Reverse biased junction diode connected through a resistance to a battery of suitable voltage. What we get? In this region, we get electrons produced, and the electrons under the field move through this conductor resistance and give a IR drop here, current I flow, IR drop. And what is electrical pulse? Time variation of potential at certain point. So here we get time variation like this. This depends upon RC value, this pulse, width, etc. Like this sharp and then this. This depends discharge of the capacitor through resistance R. So this depends on the RC value. So pulse shape becomes, means current flowing gives you electrical pulse, IR drop with the time, potential changing with the time. So this, what we do, any radiation falling on a reverse bias junction diode under the depletion layer can give you current, and this flow of current, through RC combination gives electrical pulse. So this electrical pulse can be connected to the suitable preamplifier. This can be connected to preamplifier. In fact, it is charge sensitive amplifier, charge sensitive preamplifier. So this is connected to, and then this is connected to amplifier. And then this is connected to multi-channel analyzer, MCA, to get the recording of the spectrum. So this simple junction diode under reverse bias having a depletion layer which is charge-free region. In this charge-free region, incoming radiation, any alpha or gamma or beta, whatever, they produce here charge. So I have on the passage of this, like ionized. And this electron produced can be collected. So this is a good solid state ionization chamber for counting the gamma radiation, beta particle, alpha particle. Germanium is used for the gamma ray particularly because germanium jet is large than the silicon 14, silicon 32, and silicon are used mostly for the charged particle, beta particle, alpha particle. So remember, now what is important? Important thing is this thing. What the important in the junction diode is depletion layer of certain width. This is the basis of solid state semiconductor counter. But now the research on the semiconductor counter, what they did, simply to increase the depletion layer, the best and best. To improve the system, you have to increase depletion layer to increase depletion layer thickness, to count more energetic particles. That means now the aim of the researcher to make the semiconductor detector is somehow do the research and increase the depletion layer so that more high energy particles can give ionization there. Otherwise, high energy particles will pass without interaction if layer is thin. So layer is thin, then problem. The larger layer, better the counter. So this, remember, germanium has got large noise current. At room temperature. Because the energy of voltage required to break this bonding is much less than the silicon. So at the room temperature, more germanium bonds are broken and large number of electrons are free, and they constitute the noise current at the room temperature. So what we do? We have to cool down germanium detectors. These are used at low temperature. Means using liquid nitrogen. Liquid nitrogen. The liquid nitrogen plants are very costly. When I was here in the Aligarh University Physics Department, we were having these semiconductor counters and also liquid nitrogen plant. Liquid nitrogen can be used by other departments also, medical college or the chemistry or biology people. So that was a very good plant. And one person was deputed to run that plant. And we were getting lot of liquid nitrogen. And we having 2 detectors, germanium, in our department there. After my retirement from here, the next year, man, dismantled the liquid nitrogen plant. Surprising. Because he found that one person is doing duty here and sitting here by engineer, and the use of application of liquid nitrogen was not too much. People were not purchasing from the department, and there was nobody using the liquid nitrogen in the department itself. So he dismantled. The crores of rupees costing plant he dismantled, and those liquid nitrogen, because the plant dismantled, so detectors, germanium detectors, costing lakhs of rupees, they are now useless. Nobody is using, they are worthless, because there is no liquid nitrogen. And liquid nitrogen without, we can't use these detectors. I was surprised when I returned from Ethiopia, I saw there the liquid, that detectors are lying in the dustbin type. Nobody, because there is no liquid nitrogen. Why? Oh, liquid nitrogen plant is dismantled. If you now want to purchase, it may cost 10 crores or 20 crores of rupees. There was a Philips liquid nitrogen plant under working condition. But only because one person is sitting there and he is not doing much work, others are doing work, so dismantle this thing. So remember that to use this germanium, we were having in Ethiopia also one germanium, and people don't have in the other laboratories. They are surprising, they are very costly, and my system became bad after 4 or 5 years, and the poor country, Ethiopia, we couldn't repair that because there was no money. So I was handicapped because my germanium system became useless. And I found here the germanium system already done useless by the dismantling the liquid nitrogen plant. Some politics was there. Surprising. So liquid nitrogen plant in Ethiopia are running very finely, and all the departments, they take liquid nitrogen. If you don't have any application, you can stop for some time and again generate liquid nitrogen when people require. But not good to dismantle the plant. So this liquid nitrogen plant is essential. Earlier when we were not having liquid plant, we purchased from Delhi in here, and we brought liquid nitrogen in the insulated cylinders, and by the time we reached here in Aligarh, all liquid nitrogen went out because the insulation of the cylinders were not very good, and the temperature also, carrying from Delhi to Aligarh, the whole liquid nitrogen evaporated. So when you are having a nuclear laboratory where SPG or G or silicon, particularly germanium detectors are there, you have to install a liquid nitrogen plant, otherwise you can't work. So remember now that we have silicon or germanium semiconductor diffuse junction diodes, and they can be used for the counting of charged particles or gamma rays. Remember that this thing, why in this semiconductor counter, the pulse width is much smaller than scintillator. Scintillation spectrometer. Why the pulse width is much smaller? Why the pulse width was broader here? I can show you that if the sodium iodide has got like this, germanium will have, or silicon will have this much, this width, like this width. And this sodium iodide. So this is so much width. This is negligible, very small. So The pulse width is much smaller than this. What the reason? What was the reason of pulse broadening here? Pulse broadening in sodium iodide. What was the reason? The reason, you see, at the various stage from interaction started, photoelectric effect, then photoelectron inside the sodium iodide produce scintillations, then scintillations produce photoelectron in the cathode. So process of production of photoelectron, that is statistical in nature, it will have plus minus variation because the natural phenomena are not strictly 100% the same always. If you repeat, it will change. So production of photoelectron, there is variation number. Then production of scintillations, large variation. Then passing of scintillations to the photomultiplier tube. So how much transparency, how much percentage. So there also variation. Then scintillations falling on photocathode. So emission of photoelectron, there also variation. Then photoelectron falling on the diode. Multiplication, there also may be variation. Then multiplication at the successive diodes. Multiplication by emission of electron from diodes. So all these stages from starting the interaction of radiation with the material up to getting electrical pulse, there is huge amount of variation in the number of electrons. So number of electrons finally produced at the anode of scintillation counter may have some variation, fluctuation. Suppose 10 to the power 9, 1 into 10 to the power 9, it may be 0.9, it may be 1.1 into 10 to the power 9. So this much variation means pulse height will vary, and by one radiation energy you will get many pulses of photoelectric field, and that will be giving you envelope of one energy peak. Envelope means broad. So broadening of pulse height is sodium iodide was due to that at several stages of pulse formation, starting from the interaction of radiation gamma ray with the sodium iodide up to the production of large number of electrons. At all stages, the phenomena are, I gave the expression where we have various factors. All those factors, they have variation. So when the variation is there, pulse height finally will also have variation. And this will be large variation because sometimes it is 80% transparency, sometimes 85% transparency, maybe like that. So all natural phenomena, they have statistical variation, they are not fixed. So this pulse becomes broad, very broad like this. And now what happens in the scintillation counter, semiconductor counter? What happens? Radiation came, it produced some number of electrons. Then we have some variation. And those electrons collected, current flow, pulse height is formed. Only one step. Radiation gave some number of free electrons. They are collected by flow of current through a resistance, and pulse we get a pulse height. So only one step. In this, only one step process. What one step process? Radiation giving energy to an atom and then converted to electrons. This may have plus minus only variation. One, and these are collected, so this pulse is very sharp because it has very small variation, maybe this volt or this volt or this volt. So this is called FWHM. That is full width at half maximum. When the pulse is half, what is the width of this? This FWHM is much smaller in the case of semiconductor and this sodium iodide. This is much smaller, very sharp. So any gamma ray coming nearby energy here, this will give another pulse. Any gamma ray here, this will give another pulse. But here, all the pulses will come within one broad envelope. So sodium iodide has got poor resolution. Sodium iodide, clear, poor resolution. That is delta E over E is very large. Sodium iodide delta E over E is very large, and delta E over E in semiconductor is very small as compared with sodium iodide here. That is why scintillation spectrometer is a poor resolution spectrometer, but its efficiency is larger because photoelectric effect. We have photoelectric effect with the iodine Z53 or maybe bismuth germanate. Bismuth has got 83 there. But these silicon has got that 14, germanium has got that 32. So interaction probability means here is much smaller. So efficiency is smaller here, efficiency is large here, resolution is large here, smaller here, sodium iodide. So semiconductor diode, just reverse bias diode, is used very nicely to detect the radiations which are giving ionization. Only one step means ionization. While in the sodium iodide we have many steps, photoelectric effect or Compton effect is produced, then those electrons give kinetic energy to sodium iodide crystal, produce scintillations. Those scintillations falling on the photocathode are photomultiplied to give photoelectrons, and those photoelectrons after stacking to diodes multiplied and so on. So that is multi-process, means at many stages. Pulse formation from interaction of radiation up to pulse getting is many processes. So they are all variations and we get broad pulse. But silicon or germanium, only one interaction, charge produced and collected. So it is called semiconductor ionization counter. Now I will talk only for 5 minutes more that the silicon and germanium, to improve the counter, what we do. To improve means to increase the depletion layer. If depletion layer becomes large, more energetic particles can be detected. So, silicon germanium, there are now silicon lithium drifter, germanium lithium drifter. Means lithium is compensating silicon, lithium is compensating germanium. By allowing lithium to diffuse inside the silicon or germanium crystal, we are compensating the distance, we are increasing, means the depletion layer increases much by introducing this lithium removing the silicon germanium atoms, and more that the depletion layer becomes large. By diffusing lithium into silicon or germanium. So these are called lithium drifted silicon detector, lithium drifted germanium detector. Remember, this is used at the low temperature. This can be used, but this can be stored at the room temperature. But when you use better used at the low temperature, this cannot be stored at the room temperature because depletion layer is then finished. To keep the depletion layer means you have to keep at the low temperature so that the electrons, noise current electrons are not moving, they are not killing the depletion layer. So this improvement on this is lithium drifted counter, and another improvement is now in this particularly, this is called HPGE. This is called high purity. So what is the high purity germanium? This is the latest you can say. Detector high purity germanium means, you see, germanium crystal has got some impurities. These are impurities. What are the impurities? These are called charge trapping centers. These are called charge trapping. If we don't make depletion layer, we take germanium crystal and we allow a radiation to enter. What will happen? This radiation will produce some free electrons and positive atoms of germanium will be left there. These electrons free, they can fill these are called charge trapping, means that centers, they have deficiency of electrons. These impurities have got deficiency of electron, so this free charge electron is trapped inside it. So large number of impurities atoms having deficiency of electron, if a charged particle or gamma ray radiation enters germanium, ionizing the system, producing free electrons, these free electrons are not available for counting. Why? Because they are trapped by these charge trapping centers. Impurities. Impurities having deficiency of electrons, these electrons fill those gaps and they are not available for the current to flow. So it means only the germanium crystal having large impurity is not useful for counting the radiation. If we remove the numbers of charge trapping centers, means impurity, degree. If we remove impurities which are charge trapping centers, impurities which are charge trapping centers removed, then the ionization electrons can be counted. That is, if charge trapping centers number is decreased, these electrons are available free for conduction and a current may flow like this. A resistor, electrons can flow. This is called high purity. You see, this germanium has got larger, maybe 10 to the power 16 or 10 to the power 16, 17 atoms per meter cube, per unit volume. The impurities. So the impurities atoms. These are charged epicenter. If you reduce them to 10 to the power 15, 10 to the power 14, it means you are decreasing the charged epicenter. So, making the germanium, making normal germanium as high purity by reducing impurity. Remember, this process is this task for improving germanium is very costly and too much time. So improving means removing these impurities which are present in the germanium to 10 to the power 14 or 15 like that, 10 to the power 15 or 10 to the power 14 per meter cube atoms of impurity, means you are decreasing, means charge trapping center number is decreasing. So this charge produced by incoming radiation is not being trapped and it is available for the conduction. It will give a current and you will get electrical pulse. So high purity germanium is now latest detector used for the gamma ray counting. The high purity germanium itself is the whole germanium. Large size, you encase them in the aluminum. This HPGE. Large size available. 100 cc, 150 cc means active volume of the detector, 150 cubic centimeter. So there is no depletion layer. The whole detector is sensitive for counting. You can have radiation coming here, anywhere, this producing free electrons. No multiplication needed, nothing, only collect these electrons. So whole SPGE, large size, we can have large size detector. These are small, having micrometer up to few millimeter depletion layer, maybe 1 millimeter type maximum. This is very difficult. Otherwise it is 0.01 millimeter depletion layer. Here the whole crystal is acting as a detector. There is no depletion layer because this impurity number is decreased. So this charge is not being trapped by the impurities. This is available for the conduction. A current can flow, large current can flow, and you can amplify that pulse by amplifier. So SPGE is improvement, much improvement on the germanium silicon drifted or silicon lithium drifted, silicon or germanium lithium drifted. It is much improvement because our aim was to increase the depletion layer, means active volume. At 100 cc, 120 cc or 150 cc detectors costing around 5-6 lakhs rupees are commercially available. They can be very useful for a good laboratory, but there must be requirement is there must be liquid nitrogen plant available nearby in the university. Otherwise you can't do it because the noise current is large. So you can store this at the room temperature, but when you use this detector, you have to count at the low temperature, liquid nitrogen, to reduce the noise current, to get the high pulse height of the genuine radiations. So this is the semiconductor detectors which are much better than the scintillation counter. These are used in all gamma ray and radiation research. High purity germanium gamma ray spectrometer or radiation spectrometer. So today I stop here. Next day I